Good morning, everybody. Before we get started on the stuff for today, I want to go over a couple of things. I think in terms of our mechanisms, we're getting a little sloppy. So we need to be very detailed when we're talking about a mechanism, making sure that everything is clear, okay? So I'm just going to use this one as an example. One of the first things that you should notice at the very beginning is we have a stereocenter, and you should always identify what that stereocenter is, whether it's R or S. It's going to help you as you move along. And write it down, okay? So if I look at this, I know from our conventions, right, that the carbon-oxygen bond is in the plane, the carbon-carbon bond is in the plane, this carbon is coming out, so the hydrogen must be going away. That's nice and convenient for us, right? And so we can assign priorities of 1, 2, and 3, and so this is going R, right? So we need to have the R stereochemistry, okay? Now, when we're thinking about these types of reactions, I know I've got a ether in a mixture of methanol and sulfuric acid, right? Methanol's kind of like water, so I expect sulfuric acid in that medium to dissociate into H plus and HSO4 minus, okay? Huh? Well, it is an epoxide, but an epoxide's an ether, right? It's a special ether. I'm giving just the more general definition, right? And so we know that we're going to have a situation where we're going to have H plus and HSO4 minus, okay? And be very purposeful when you draw your charges. So a lot of you are drawing charges that are kind of distant from where they really belong, and so they're there, but I don't know really where they belong, okay? So we want to be careful about that. And we protonate. Now, a lot of you are forgetting to draw your arrows. Whether it's a reaction arrow or an equilibrium arrow, they need to be there in a mechanism because it tells us if an equilibrium lies to the right, to the left, or if it's a mixture, right? Here I'm going to use an equilibrium arrow, okay? And we're going to end up with a protonated epoxide. Still have my stereochemistry, right? And my formal charge needs to be here. Now, some of you on this one had the formal charge up on the hydrogen, or it looked like it was on the hydrogen. Let me say it that way, okay? I don't really know where it was at, but it really belongs on the oxygen, right? So let's draw it where it makes most sense to draw, okay? And now I know that I have my methanol in there that's going to function as my nucleophile, and it needs to attack one of the two carbons and open up the epoxide. Which one does it go after? It goes after the most substituted, of which nobody made an argument in their mechanism for why that has to be the case. You just drew the arrow, okay? Mechanisms can also involve some words. Explain why you choose when there's more than one option, okay? It is what it does in acid, but is that the explanation? That's an observation. But the explanation is because this is the weaker sigma bond, right? You tell me. Under acidic conditions, will it attack the least substituted? No, but under basic conditions, we do, because the nucleophile is negatively charged under basic conditions, or at least there's a lone pair, and there's no proton on the oxygen of the ether, so it attacks the least substituted, which is the least sterically hindered. Now, in doing this, right, be very careful with your arrows. Make sure that I can tell that it is a double-headed arrow. A lot of arrows that I saw were like, is that a single barb? Is that a double barb? Be more purposeful with how you're drawing, okay? Now, in doing this, what's going to happen to the stereochemistry? It is going to invert, and so I know I started with R, I better end up with S, right? Now, here I'm going to draw just a single arrow. I'm not going to draw an equilibrium, and why not? Why can't I? Okay, three-membered ring is strained. It's hard for it to go back, right? So I know it's going to lie to the right, and it's going to lie so far to the right that I can ignore the reverse reaction, okay? Is it reversible? Of course, all reactions are reversible, but it lies so far to the right here, okay? So I know that I'm going to have this connected to this carbon, right? And I know I'm going to have OHCH3 as an intermediate, right? I'm going to have a methyl group, and I'm going to have a hydrogen. Now I'm just drawing that in as stereochemistry to start with. Now we have to check that stereochemistry. Is it S? This would be number 1, number 2, number 3, and it's going in the S direction, so I'm fine. Some of you had R going to R. Some of you had it correct, but I think just got lucky. Okay? So be purposeful. Are we done? No. Not yet. This is an intermediate, and so what happens then is our conjugate base, I take HSO4 minus as the conjugate base because I told you it was catalytic and you have to get sulfuric acid back. But if you'd also used methanol as a conjugate base to do this, it would be perfectly acceptable. Okay? And now this one I do have to draw as an equilibrium. Okay? As we're going through that. Be very careful. I think a lot of you are trying to do the mechanism completely in your head and just drawing down bits and pieces of it, but the mechanism needs to be complete. Also, one of the things that I saw that will really get you into trouble is combining steps. So for example, some people were showing the protonation of the ether with the nucleophile attacking at the same time. Okay, it's a stepwise process. It's protonation followed by nucleophilic attack. Okay, and that's very important to have that down correctly. Yeah, Aubrey.
The OH right there, did it come from, is that the hydrogen that was on this carbon?
This one?
No. Okay, it was all right, never mind. Okay, we're good.
We're good? All right.
I forgot where it protonated.
Okay.
Can't read apparently.
That's okay. That's all right. So tonight in this room, Tech 411, 5:30 to 7:30, bring the stuff. We're going to go over it, okay? People will go to the board and work on it. So we will be working on that then, and I'll probably have another one to try to accommodate some other time periods. Okay? All right. So, can I, well, I mean, what would I be YouTubing? I mean, people are going to just be working at the board.
Okay, never mind.
I mean, it's kind of a workshop kind of thing. It's not, that was the last written word lecture. Yeah. So I've got it graded. I'm going to hand it back to you today, but I want you to bring it tonight or whenever we do the next one. But also what I'm going to do is I'm going to give you a little chance of redemption. So I've got a bonus quiz that you can work on your own, bring it back on Friday. This has to do with that pKa paper because I still think we're having some pKa issues. Okay? So answer these, and I'm going to give you 2 points for each question. There's 5 questions, so you can get up to 10 additional bonus points that can go to helping offset some of that. Does that sound fair? Don't be scared. All right, so today we're going to get into chapter 13 and we're going to start talking about allylic systems. So today we're going to talk about allylic radicals and allylic cations. What do I mean by allylic? Double bond by itself is vinyl. Okay, so we have a pi bond, that's true, but what is it? Okay, so it's a double bond and then a sigma bond, and that sigma, whatever that carbon is that's attached to that is the allylic position, right? So it looks something like, if I had my pen with me. So as Yusuf said, there's a pi bond, but that by itself is vinyl. When we add anything out here, this is the allylic position, okay? So that is an allylic carbon. And you can have allylic radicals, you can have allylic cations, you can actually have allylic anions, and these things are more stable than you might expect due to resonance, okay? And so your resonance rules are very, very important here. I'm not going to review them because we've gone over resonance an awful lot in 255, but you need to keep refreshing yourself on resonance. Resonance is going to play a big role from here on out as we talk about mechanisms of a variety of different reaction types, okay? Also, I'm going to pincast some problems from Chapter 12. I'm going to go through and pick a few problems. I'm going to pincast them so you can see some examples of worked problems. And check Blackboard for that this weekend. I'll have those pincasts up hopefully late Saturday, if not sooner. Okay? But let's think about some of the things from Chapter 12 real quick. If I take a Grignard and an aldehyde, what do I get? You get a secondary alcohol. If I take a Grignard and a ketone, what do I get? If I take a Grignard and formaldehyde, what do I get? Not Aubry. What do I get? Yep. I get a primary. That's right. If I take a lithium reagent and carbon dioxide, what do I get? Carboxylic acid. That's right. Okay. So in all those cases, we were adding a carbon nucleophile to an electrophile that was a carbonyl, right? And so we can do a lot of that. And I'll be pincasting somewhat on that again this weekend, so keep an eye out for that. So conjugated systems, we've got several examples. All of these are more stable because of resonance. So for example, if we look at 1,3-butadiene, okay, we say that that is a conjugated system. Looking at that by itself, how do I know that that's a conjugated system? What did we learn in 255 that signifies that that's a conjugated system? What do you think? What does it mean to be conjugated? You're on the right track. Go with it. More than one form meaning what? Yeah, we can form resonance structures across multiple atoms, right? And so if we look at the 1,3-butadiene, and I'll draw it up here, we can draw multiple resonance structures for it as they've shown you there, right? And why can I draw multiple resonance structures of it? Notice I have a double bond, single bond, double bond. And anytime we have that motif, we know we have conjugation because each atom in the system has what on it? Well, I don't have a double bond here. I have pi bonds, so each atom has what? What do I need to make a pi bond? What makes the pi bonds? Well, there is sp2 hybridization, but that's not the orbital that makes the pi bond. The pard? The p orbital. Each one of these atoms has a p orbital on it. And those p orbitals actually overlap with one another. And that's what makes it conjugated. This is really one pi system. It isn't two double bonds in reality. It's one system. And we know that because we can draw multiple resonance structures for that. What would happen if I put another carbon in between here and here? It wouldn't be conjugated anymore, right? We would have a pi bond, and we would have a pi bond that are totally separate from one another. They're not communicating or talking. Huh? That's right. I can't draw resonance structures anymore because then I'd have p orbital, no p orbital, p orbital, p orbital. And so I can't get them to communicate with one another. But here it's p, 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 right? So they can all overlap, and we can draw resonance structures for them, okay? Now, you can see we have three resonance structures shown here. Which one is the major contributor, the top, the middle, or the bottom? Why? No charge separation? That's right. So does that mean that the other two are what? What does that mean? They are what kind of contributors? They're minor contributors. Does that mean we can ignore them? No. They contribute to the overall resonance hybrid, even though this is the major contributor. And that means that this molecule is more stable than you would expect for 2 pi bonds. Okay? If I took 2 pi bonds and I put some carbons in between them to where they couldn't communicate, it would be less stable than that molecule, okay? Even though it's larger. We can also have the same thing with radicals. We talked about radicals in chapter 10. These are allylic radicals. What can you tell me about these 2 resonance structures? Where must the radical be? On the terminal carbons. Where can it never be? It can never be in the middle. There is absolutely 0 electron or single electron density at the middle carbon. It's either on the left or the right terminal carbons, right? How about the carbocation? Same thing, the cations and the ends. And the carbanion? Same thing. And so we can draw resonance structures for all of these systems. And so they are stable. We are going to see that actually there is some special chemistry that goes on with these allylic systems in this chapter. That's, I think, pretty important to have a grasp of. Okay? So, how else can I represent that system? I've got a resonance structure on the left. I've got a resonance structure on the right. Are either one of those resonance structures the true story? No. What does the system really look like? Okay, the hybrid, right? The hybrid is what we're after. And the hybrid, right, is a situation where we have 3 atoms. I don't know why these p orbitals are showing up so funky, but they are. Okay, so we got 3 p orbitals, and there's an electron in each one of them, right? That's what the system looks like, okay? Which gives rise to something like that. That's how we would depict that in shorthand, okay? What does this dashed line mean? Yeah, we got a partial double bond between carbons 1 and 2, and we got a partial double bond between carbons 2 and 3. And what does this mean in the middle? The radical is delocalized over the whole system. And since I know my resonance structures really well, I know that the radical spends half its time, that's actually a bad way of putting it, but it has half its density here and half of its density there. Okay? And 0 of the time is it at that central carbon. Okay? Now, if we think about alkenes, we know that we can take an alkene and we can add bromine or chlorine across that carbon-carbon double bond and get a dihalide, right? We learned that. In the absence of free radical conditions, that's what happens. So if Gabriella came to my lab and she took this alkene and she dripped into it bromine, all that would happen is the bromine would add across the carbon-carbon double bond and she would end up with a dibromide. Okay? Just as we expect addition chemistry to occur. And that's good chemistry, right? Because everything that we put in comes out in the product. However, let's suppose she's working in my colleague's lab across the hall and she's working next to the window and there's this intense light coming in from our southern sun, right? It turns out that she might get a different product. How is this product different from this product? There's still a double bond. And what else is different about it? One less halogen, okay? And what else is different about it? If she went over there with some pH paper between both reactions, what would she notice? This would get to become low pH or more acidic, and this, no pH change really at all, right? We're not generating any HX, okay? This is called an allylic substitution reaction. What are we substituting? What for what? Okay, we're going to substitute the hydrogen for what? A halogen. That's exactly right. It's a substitution reaction. At this point, the substitution reactions that you know are SN1 and SN2. This is neither. This is a free radical mechanism. It is a substitution reaction that does not involve a good leaving group. H is not a good leaving group, right? So therefore, we are not going to push arrows like an SN1 or an SN2, even though it's got the word substitution in it, okay? So if we do this chemistry where we have a really low halogen concentration, increase the temperature really high, or add a free radical initiator, we can get this type of chemistry to occur. If we add a lot of X2, do this at room temperature, no free radical conditions, that should be a V there for H nu, we will get the addition chemistry. So when you look at these problems from now on and you go, hey, I see an alkene, I see a halogen, you need to stop and go, is this going to be an allylic reaction or just a simple addition reaction? You've got to know the difference. Are we under free radical type conditions, or are we under conditions where just the normal addition process should take place? So you're going to have to evaluate what your conditions are, and conditions are going to be becoming more and more involved in the mechanisms. In 255, the conditions, you didn't really have to spend a whole lot of time evaluating them because we were just talking about one set of things at a time. But now it's going to start becoming more and more important. So as we know, all free radical reactions have three fundamental steps. What are they? Initiation, propagation, and termination. And we can only have one propagation step, right? No. We can have multiple propagation steps, right? And we can also have multiple termination steps. Here we've got a situation where we're taking chlorine and we're taking propene. And so the initiation step is if we're at high heat or under intense UV radiation. I don't know why my V's aren't showing up today, but they're not. We break the chlorine-chlorine bond. In what kind of fashion? What kind of arrow would you use? Single barb, right? So that's homolytic or heterolytic? That's heterolytic. That's right. So at heterolytic bond cleavage, we end up with chlorine radicals. Okay? Now, chlorine radicals do not have an octet, so they're very reactive. They come in and they react at the allylic position. Okay, notice we're using a single barbed arrow. That is actually a single barbed arrow that is just projecting badly. Okay, so single electron, single electron, single electron. We end up with a molecule of hydrochloric acid, and we end up with an allylic radical, or an allo radical, as they call it here. Okay, why does the chlorine radical abstract this hydrogen and not this hydrogen or this hydrogen? It is a weaker bond. Why is it a weaker bond? Okay. Well, that's true. You're telling me the true facts. But give me an explanation. Why should this bond be weaker than this bond? That's right. It has to do with the allylic stabilization that you get in the product. Okay? So this bond is in, if you will, kind of like conjugation with the system, and so that makes this weaker. And so you can end up forming this allylic radical that's more stable. If I remove this hydrogen, for example, can I draw resonance structures that stabilize it? How about this one? This one. But any of these, I can, right? Any of these that are on the allylic hydrogen, or excuse me, the allylic carbon, I can. So now we end up generating an allo radical. Okay? That allo radical then reacts with chlorine to give me the product, allo chloride plus the chlorine radical. What happens now with this? Goes back up, and we continue in these propagation steps until what? Till we run out of what? When our starting materials start to approach zero, all of a sudden what happens to our radical concentrations? Now, they increase really quickly, right? Remember, we don't have very many radicals at all while we have our starting materials. But once the starting materials deplete, now my radical concentration in the system goes up. And then they start to terminate. That's right. And so what are some possible terminations? I don't have them up here, but just give me some examples. Okay, I could have two chlorine radicals coming together to form CO2. What else? Okay, so I could have a chlorine radical reacting with the allo radical. And what else could I have? I could have two allo radicals coming together to react to form a carbon-carbon bond. And if you look at the trace contaminants in the reaction, in fact, you'll find all of those. You'll find a little chlorine. You'll find a little bit of the two allo radicals that came together to form that product. They're there in small quantities, but it happens because of termination. Now, I want you and your partners for just a minute to think about this. If we do this exact reaction, but we spend $5,000 buying this molecule, where this carbon and this carbon alone is labeled with carbon-13, tell me where the carbon-13 is in the product. So we take that, we mix it with chlorine, we shine a bright light on it. Gabriella then goes and does a C13 NMR. What will she see? Think about it for a minute, and then we'll work through the mechanism. So we've just got propene with the allylic carbon C13 labeled, and only that carbon C13 labeled. Oops, I'm sorry.
You want to know where you see that?
In the product, where does that C13 end up? How am I going to solve this problem? Time's up. How am I going to solve this problem? I'm going to draw the mechanism. That's exactly right. So I'm going to take a quick little shortcut, and I'm going to assume that we have the initiation already in place. You all know that mechanism. And so we have propene, where the allylic carbon is labeled with a C13. And so I'm going to start at the first propagation step. Let me draw this out. How do I draw that? Single barb. Now what?
Now that product goes and reacts with 2 more CLs.
Okay. It goes back in, right? All right. If we think about this, if Gabriella goes in and runs the C13 NMR, she should see how many C13 peaks? 1. And where would it approximately be? It'll be somewhere under 100, but it's a allylic that moves it down a little bit, so it's going to be 60-ish. Good ballpark for me, right? So that's where we would expect to see it, right? However, Gabriella goes and runs the C13 NMR, and what she finds are 2 peaks of equal intensity, one that's around 60-ish and one that's in the alkene region. In other words, she also finds that product, and it's equal. She ran a special experiment where she can actually integrate the C13 peaks, and she finds out that it's exactly 1-to-1. Aubrey, what's the reason? Because of the resonance of this intermediate. It doesn't, does it? That's right. In reality, this is in And this carbon can attack chlorine to give this product, and this carbon can attack chlorine to give this product. And as a result, it looks like that C13 has moved throughout the molecule. Hadn't moved a bit, but it's just the pi bond orders how things are done, right? This is a classic experiment to show the importance of resonance structures. You can actually go and do this experiment. I've done this type of experiment before, where we were interested to see if we were going through something like a free radical mechanism. And you can actually watch and see how the C13 label moves through the molecule, okay, due to these types of mechanisms, okay? Does that make sense? Does that show the importance of resonance structures? You bet, right? We know that our radical stability order, we learned this last semester, right? Tertiary is more stable than secondary, more stable than primary, more stable than methyl. But notice allylic radical. It's more stable than all of those. And why is that? Why is this more stable? Resonance. This looks like, if you ignore the pi bond, this looks like what type of radical? It looks like a primary radical, but it is not a primary radical, right? It is not this at all, but if you look at the stability, it is an allylic radical, and it is a lot more stable because of the resonance structures, okay? Now, it's very, very difficult to do allylic substitution using liquid bromine. If you go back a couple of slides, I said we had to be under free radical conditions to do allylic substitution, and the halogen concentration had to be what? High or low? It had to be low. So Sarah Polly comes in to do this reaction. She's got her alkene, she's got bromine in a burette, and as she adds the bromine to the reaction, what's the concentration of bromine right where the drop hits the reaction? It's really high. So what's going to happen? It will do some addition. Absolutely. It will compete. So addition always competes with allylic substitution when you use chlorine gas or molecular, liquid bromine. Okay? So how do we keep the concentration of our halogen low at any given moment? We use NBS. Okay? I'm not saying you can't do this chemistry with bromine and chlorine. You absolutely can, but it's an engineering problem. Because a burette, a drop-in, the concentration right there is really high, and it competes. How do you deal with that? There are engineering ways to solve that problem, and they do this in the chemical industry. But on a laboratory scale, I don't have a stir bar that spins fast enough. I don't have equipment that handles the dilution like I really need to, okay? But what I do have in my toolbox is a reagent that we've talked about before, NBS, N-bromosuccinimide. And it turns out NBS is not bromine. So I can take NBS and my alkene, which has these two allylic carbons, right? And I can mix them together, and guess what? Nothing happens until I initiate the reaction, okay? So now I can either add a peroxide or shine a really bright sun lamp on it and get the chemistry to go, and I can get almost exclusively allylic substitution to occur at the expense of addition, okay? NBS does this very, very well, okay? And so it allows us to do the chemistry. It keeps the bromine concentration almost, for all practical purposes, at zero, okay? And it does generate some bromine in the process, and we'll see how that happens, okay? And so if you really want to avoid addition across the alkene, you need to use something like NBS, okay? Now here's the mechanism. The first thing that happens is the nitrogen-bromine bond in NBS is actually fairly weak. And so when you shine a bright light on it or you use a peroxide initiator, this nitrogen-bromine bond will actually cleave to give you a nitrogen radical and a bromine radical. What do we know about bromine radicals? Stable or unstable? As far as radicals go, they are stable. All radicals are reactive. That's true, right? But, well, there's some even exceptions to that statement. I shouldn't be so broad. But the bromine radical is reactive. Yusuf is right. But when I compare it to, say, chlorine radical, I know it's a lot more stable, right? So I have this relatively stable radical. So it can only really abstract the most reactive hydrogens, right? It's not going to react with any of these hydrogens out here because they're not allylic. They're not the most reactive. So the bromine radical comes in, reacts using our single barbed arrows, and I end up with the stabilized allylic radical. Okay? This radical then reacts with the bromine that we get from NBS and gives me the product, and the bromine radical which continues. Now, what's your question at this stage? What question should you be asking me at this stage? What shortcut have I taken that I shouldn't have?
Well, you extracted more Orbitals. You got BR2 somewhere.
I did. Where did the BR2 come from, right? I say it comes from NBS, but did I tell you how that happens? Not at all, right? And that's what I'm going to tell you now. How do we get bromine from N-bromosuccinimide? Well, it turns out this is kind of a clever little mechanism. NBS, this nitrogen has a lone pair, which is, by definition, a Lewis base. What is HBr that just got generated in the reaction? An acid. Is it a strong or a weak acid? It is a strong acid. And so what happens is the NBS gets protonated to give me this nitrogen that's positively charged, which makes this bromine nucleophilic or electrophilic? Electrophilic. And so now bromine minus comes in and reacts with the electrophilic bromine, giving me succinimide and Br2. Ain't that sharp? Because this step right here gave me the HBr that I needed, so I've got the radical generated, right? And that got consumed almost immediately, giving me exactly 1 molecule of Br2. So my concentration is going to be low, because as soon as I generated that bromine, it's going to react with that radical, right? Aubrey?
Is there a way to enter your reaction, get the succinimine out and then react it with BR2 to get your NBS back?
You can regenerate succinimide to make NBS. That's possible. It's so cheap that most people don't, at least on a laboratory scale. The cool thing about this is NBS is typically soluble in things like methylene chloride, things that these reactions are typically running. Succinimide only has moderate solubility, and so it usually crystallizes out and falls out of the reaction mixture as the reaction is proceeding. Okay? So isn't that neat? We need to keep our bromine concentration low, which means as soon as it's generated, it's consumed. And so we use this reagent that can get the free radical reaction started and generate the bromine that we need almost simultaneously. Okay? Not quite, but almost simultaneously. And so the bromine concentration at any given moment is essentially 0. And if you run these reactions, you will find, okay, and I've run some of these reactions before, I could never detect by NMR addition chemistry. Doesn't mean some didn't happen. I'm just saying I couldn't detect it. I got, for all practical purposes, 100% of the allylic bromination in these reactions. If I tried to do this reaction by adding bromine, I would get about a 60% addition and about 40% allylic substitution. And that would get you fired in industry. Okay? So, NBS is a very good reagent for this allylic bromination, as we call it, of these allylic systems. Okay? Now, we're going to have to talk a little bit about molecular orbitals. You all talked about orbitals in Gen Chem, right? And that was your favorite topic, right? It was not your favorite topic. The cool thing about organic chemistry, we're only dealing with p orbitals and s orbitals for the most part. So orbitals for us is very easy to deal with. Okay? We can deal with those really, really easily. Okay? And we also use what's known as frontier molecular orbital theory. Okay? FMO. Frontier molecular orbital theory. And it's because organic chemists are lazy and we don't like thinking about orbitals all the time. And so we have this process where we only deal with the orbitals that are actually involved in the reaction, and we ignore everything else. Right? When you drew those MO diagrams for things in Gen Chem, you took all the atomic orbitals and you generated all the molecular orbitals. In organic chemistry, you just take the reactive atomic orbitals and make the reactive molecular orbitals. Okay? What do we know about s orbitals in organic chemistry? Usually not involved in much, right? So we kind of ignore it. So if we think about our propene system, each one of these carbons has, as I mentioned, a p orbital, right? And there's an electron in each one of those p orbitals. Each one of these carbon atoms has a single p atomic orbital. And these are the only orbitals that I need to take into account. All these sp2 orbitals are part of the sigma system, and they don't do a darn thing for us. So ignore them, right? And so what do we know about an orbital? Why do I have these lobes as orange and blue? What does that mean? Blue and, pardon? Close. What have I not drawn on these orbitals? The sign, right? Not charge. Sign. Those are not charges. Those are arithmetic symbols. What happens if Obry comes in and takes +1 and adds to it -1? What does he get? He gets 0, right? This stuff for molecular orbitals comes out of physics. I know from what I've heard your favorite subject, right? And wave theory. What happens if I take a wave and I have a wave that's out of phase with it and they come together on a wave? Have you all done the wave table? You haven't done a wave table? You have done a wave table? Huh? Sounds familiar? You have the pool of water and you see how the waves ripple and, right? You know what I'm talking about? So if I take two waves and they're in phase with one another, what happens to the resulting wave? Bigger or smaller? Bigger, right? That's what happens in a tsunami, right? Okay. So if I take two waves that are in phase, they add up and make a bigger wave. What happens if I take two waves that are out of phase? They cancel each other out. These orbitals are really out of wave theory because electrons can be both particles and waves, right? The dual nature, okay? So what's going to happen if Megan takes a wave, and this is an orbital that looks like this, and adds to it a wave that looks like that? She adds those two things together. What happens to those waves? They cancel out, don't they? Right? And there's no wave there. That's what we're looking at here. And there are three possible combinations for these waves. Because I've got three atomic orbitals. Make sure I've got time. I've got three p orbitals on those carbons, right? And I'm just going to shade them for the phases. So we've got shaded and unshaded. Think of it as plus and minus. Doesn't matter. You can use check marks. I don't care what you use. Just make the two lobes different. Use your crayons. I don't care. All right? You can imagine taking all three of these and adding them together such that all the phases line up. And then when you do that, you get this atomic orbital, where all the one phase is on one face, all the other phases on the other face. And this is what it looks like if you use my $1,200 piece of software. Okay? And that's one molecular orbital that I can put two electrons in. Okay? Now, you can also imagine adding them together where I've got this phase, the other phase, and this phase, and so it cancels out in the middle, right? And so you would have this, nothing, and then this. That's the middle one. Notice how many electrons are there. One. This is the orbital where the single electron or the radical resides. This is where the pi bond resides. The pi bond can either be here or it can be here, right? And that's why we have it looking like this. So those two electrons can be across all three atoms. This single electron can only be where and where? At the ends. It can never be here. Why? Because there's no wave to put it in, right? There's no orbital. And then, of course, the other possible combination is this one, where you have two nodes, okay? So here we have 0 nodes, we have 1 node, and we have 2 nodes. So every time we go up, we have to generate a node, okay? This is molecular orbital theory. And we will continue talking about that some on Friday.